Hi class, let's take a look at problem C. Now in this case, let me just define the vectors. And I'm just going to go with V1, or V1 is equal to the vector 2, 4, 6. And V2 is equal to the vector 1, 2, 3. Now this case is a little bit hard to actually visualize. This is because, well, if you notice on this one, your vectors are parallel. So let me just make a statement here. The vectors are parallel, or the direction vectors. And I'll just say since, well, the values of V1 is equal to 2 times the values of V2, which is going to give us the vector 2, 4, and 6. Now, for parallel lines, one of the conditions is that, well, your vectors are parallel. In this case, we have parallel vectors. The last portion, you have to check if these are actually parallel, or you could end up with the same line. So you're going to check for an intersection. Now, if you look at the intersection, you're looking at the x's, the y's, and your z's. And in this case, your x's are going to be 1 plus 2t. So 1 plus the values of 2t. This is equal to 5 plus s. So 5 plus the values of s. Your y's are going to be negative 2 plus 14. This is equal to 6 plus 2s. And then your last one is 3 plus 60. This is equal to negative 9 plus 3s. And then we're looking at equation number 1, 2, and 3. Okay, so let me solve equation 1 for t. So solve 1 for t. And you technically have 1 plus 2t. This is equivalent to 5 plus s. And then let me start with subtracting 1. And then we have the values of 2t. So 2t. This is equal to 4 plus s. And let me divide by 2. It's going to create fractions, which is what I was trying to avoid. But in this case, you're going to end up with 2 plus the values of s divided by 2. Okay, at this point, let me plug it in into equation 2. And you do have the picture of what this one looks like. And when you have parallel vectors, you have to double check to make sure that, well, you do have the same line, or if there's no intersection, then yes, the lines in R3 happen to be parallel. So in this case, let's evaluate. We're looking at t is equal to 2 plus s over 2 into equation 2. And equation 2 says negative 2 plus 4t, it's equal to 6 plus 2s, or negative 2 plus 4 times 2 plus s divided by 2 is equal to 6 plus 2s, or negative 2 plus 8 plus 2s, this is equal to 6 plus 2s, or in this case, 6 plus 2s is equal to 6 plus 2s. Here is where you would find a contradiction, and you would conclude that yes, the lines are parallel. But in this case, if you subtract the 6, and if you subtract the 2s, we're actually gonna find out that, well, not a contradiction, but we end up with the statement of 0 is equal to 0, which is true. Now, what this means is that the lines intersect at every single point. So the lines at all points. And then let me just summarize what we have. So we do have parallel vectors. And then we don't have distinct lines. We have the same line. And this is because we found that the intersection occurs at every single point. So the intersection occurs at every single point. And that's pretty much it. The only thing we can conclude is that we have technically parallel vectors. We don't have distinct lines. So in this case, I'm just going to rewrite it as we have the same line. And you can see the picture here. So we don't have multiple lines. They happen to be the same. This is what it looks in Desmos. So you're given two lines, but in reality, it's the same. So technically, we just have the same line. And the only thing that we have is parallel vectors. So the direction vectors happen to be the same. If we had found a contradiction here, then in that case, you do have two lines in space that happen to be parallel. But in this case, we're given the same line.